Okay, good morning everyone. Today I'm going to present the manual hand calculation for the flow sensor linearization. The given non-linear equation is the ln x plus x equal to 3, where x is the character flow parameters. To solve the equation, I use the fixed point iteration method. First, the equation is rearranged into the fixed point form, which is s equal 3 minus ln x. So the iteration formulas become x1 plus 1 equal 3 minus ln x1. The initial guess is x0 equal to 2.0. The calculation is done using the 4 decimal place, and stopping condition is when the approximate error is less than the 0.05%. The error formula used is EA equal to x new minus XO divided by x new multiply 100%. For the first iteration, x1 equal to 3 minus ln 2.0000 and x1 equal to 2.3069. And the error for this iteration is EA equal to 30.36%. Since the error is higher than 0.05%, the iteration continues using the latest value of x equal to 2.20x1. At the iteration 9, with an approximate error of EA equal to 0.0226%. Since 0.0226% is less than 0.05, the calculation is stopped. Therefore, the final corrected flow parameter is x equal to 2.20 at 1. So for the conclusion, the fixed point iteration can solve the non-linear equation step by step. However, for a real flow sensor system, the Newton-Raphson method is the more practical because it converges faster and requires fewer iterations. Okay, this method is used to solve the nonlinear equation ln x plus x equal to 3. First, the program uses fixed point iteration where the equation is rearranged as the x equal to 3 minus ln x. The initial value is x0 is equal to 2, and the iteration continues until the approximate error is less than 0.05. Next, the code that we use is the Newton-Raphson method. For this method, the function is fx equal to ln x plus x minus 3, and the derivative is the f prime x equal to 1 divide x plus 1. Both method calculate the roof step by step, but the Newton-Raphson is faster because it uses the derivatives to reach the answer with a fewer iteration.
My name is HADIID, and today in this video we are looking on how to perform a numerical interpolation to estimate value between known data points. For this question, we are examining an ADC analog to digital converter calibration scenario when we have a set of discrete measurement. Interpolation allow us to predict what the output should be specific input value that wasn't directly measured. In this example, we want to estimate digital count for a voltage of 1.25 volt. So first thing first, when we want to start to write a code, we have to look at the question. So the question got V, and C. So all the value has been given, so you just put on your code 0.0, 0.5, 1, 1.5, 2, 2.5 for the V, and below that we put X is 1.25 V. So for the Newton divided difference method, we put Xn inside of the bracket 0.5, 1.0, 1.5, and 2.0. And for Yn, we put 102, 205, 309, 415. For the Newton interpolation formula, for Newton result equals to dd 1, product term is 1. For J, we put 2, n. For the Lagrange interpolation method, we code xl equals to xn, yl equals to yn, and m equals to length xl. Lagrange result equals to 0. As a result, if we can see in the common window, we have the answer of Newton divided difference result, which is 256.8125. And for the Lagrange interpolation result, we have 256.8125, which is the same. The results are the same. So for the graphic representation, the blue circle represent our given data points, while the red marks is our estimate at 1.25 volt. You can clearly see that our estimate fall exactly between the measure point, which is at 1 volt, and 1.5 volt, which align with our expectation. For in summary, we have utilized two powerful numerical methods, which is Newton divide difference and Lagrange interpolation, which is to calibrate ADC model. This technique is invaluable in engineering when you need it in infosystem behavior between experimental data points. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Azamudin bin Azhar. My number metric is S72980. Today we are solving a system of three linear equations using two different numerical methods: Gaussian elimination with partial pivoting and the Gauss-Seidel method. First, Gaussian elimination. To prevent large rounding error, we use partial pivoting by swapping the first row with the third row to put the largest coefficient 2 on the main diagonal. Through row operation, we eliminate the elements below the pivots, resulting in this upper triangular matrix. Using back substitution, starting from bottom row, we successfully find our solution. X1 equal to minus 1.003, X2 1.001, and X3 equals to 3.001. Second, the Gauss-Seidel method, we arrange the rearranged diagonal dominant equation to isolate X1, X2, and X3. Starting with an initial guess of all zeros, we iteratively update each variable using the most recent values available. By iteration 2, our values are tracking toward the exact solution, yielding x1 equals to 2.3806, x2 equals to 2.8696, and x3 equals to 0.3749. Moving on to the importance of partial pivoting and our final comparison. Looking at our initial system, the first coefficient 0.003 is extremely small. Dividing by such a tiny pivot can lead to massive round of errors and numerical instability. By implementing partial pivoting, we automatically select the largest available pivot, significantly improving the accuracy of our calculation. Finally, let's compare our result after 2 iterations. As shown in the table, Gaussian elimination quickly converged to our highly accurate solution. X1 is approximately 0.113, X2 is 1.001, and X3 is 3.001. Meanwhile, the Gauss-Seidel method is still in its early stage of iteration, yielding 2.3806, 2.8696, and 0.3749. This highlights how direct method with pivoting can provide highly precise solution faster for this type of shifter. This MATLAB output demonstrates the numerical solution to our system of linear equation using two distinct approaches. First, Gaussian elimination with partial pivoting. As seen in our initial matrix, the first pivot element is a tiny 0.003. To prevent massive run of errors and numerical instability, MATLAB automatically implement partial pivoting, swapping row 1 and row 3 to place the maximum absolute value 2.0 as the pivot. After a second row swap during forward elimination, we obtain a stable upper triangular matrix. Back substitution yields our exact solution x1 equal negative 1.003, x2 equal 1.001, and x3 equal 3.001. Second, the Gauss-Seidel method versus the exact solution. Using iterative approach with a starting guess of all zeros, iteration 2 yields values that are still quite far from our targets. This directly with the MATLAB /exact solution, which match our pivoted Gaussian elimination perfectly. This underscore that why iterative method need more time to coverage. Direct elimination with proper pivoting give us precision instantly. Thank you.
My name is Amira Binti Azizan, X98882. I want to present for the chapter 5. For the manual solution, we solve the DC motor speed problem based on the differential equation ds equal to ds over dt equal to 300 minus 2s with the initial condition as s0 equal to 0. The motor speed was calculated from t equal to 0 to t equal to 0.8 seconds using a step size of h equal to 0.2. Two numerical methods were applied, namely the Euler method and the Hussin method. For the Euler method, the motor speed at the next step is estimated using only the slope at the current point. This method is simple and easy to implement, but its accuracy is limited because it relies on a single slope estimation. For the raster method, two slope estimation are used in each step. By considering additional information within the interval, this method provides a better approximation and generally produce more accurate result. After completing all the calculation, the result from both methods were compared with the exact solution to determine their relative true error and evaluate their accuracy. Next, for the MATLAB coding part, a program was developed to automate the calculation for both the Euclid method and the raster method. First, the differential equation, interconnection, step size, and time interval were defined in the code. MATLAB then performed the numerical calculation step by step using the formulas for each method. The exact solution was also included in the program so that the numerical result could be compared directly with the actual values. The output was displayed in a table showing the estimated motor speed and the corresponding error for each method. Based on the MATLAB result, the Euler method produced a motor speed of 130.5600 at t equal to 0.8 seconds, while the raster method produced 117.9279. The exact solution was 119.7155. Therefore, the raster method gave a result that was much closer to the exact solution and had a smaller error compared to the Euler method. This shows the raster method is more accurate for solving the DC motor speed problem. Next is comparison the Euler method and raster method. At t equal to 0.8, the exact solution for the DC motor speed is 119.7155. Based on our finding, the raster method is significantly more accurate than the Euler method. Raster method managed to approximate the speed at 117.9279 with a very low error of only 1.49%. Meanwhile, the Euler method was less precise, yielding 130.5600 with a much larger error of 9.06%. This happens because raster utilities utilize two slope evaluation per step to improve its estimation, where Euler only relies on one internal slope.